So I'm happy to present GLUE, Generative Latent Unification of Expertise-Informed Engineering Models. So the last years have seen much progress in Gen AI models for engineering, but much of these tend to be for specialized domains. And so the question of how to scale this to the full complexity of real-world engineering problems still remains sort of open. Now, the current predominant approach to do this is to use a single powerful monolithic model and try to scale that for increasingly larger, more complex engineering problems. So instead, what we advocate for in this paper is a distributed approach. And that means we have one generative model per subsystem or per domain. And in this example, that could mean a pre-trained model for a wing, one pre-trained model for the internals, and one for a fuselage. And each of these must expose a low-dimensional latent Z, which is very common in generative modeling. And that comes with three major advantages. So first off, each subsystem model is allowed to keep the right inductive biases. So whatever works best for that specific domain. So for example, wing aerodynamics and component placement are two pretty different problems. And if we want to build a good generative model for each of these might require vastly different architectures, different losses, or problem parameterizations. And so with the distributed approach, we allow for that. Second, this distributed approach sort of mirrors how large engineering projects and companies are actually organized into specialized teams. And then third, this allows for reusing of third-party pre-trained subsystem generators. So for example, one could use an open source wing model trained by a government lab and use that without modifying it. But if we want to actually do this distributed approach, that means we need to explicitly coordinate between the subsystems. And so what we propose here is what we call generative latent unification. And what that means is that we coordinate between the latent spaces of the subsystem models with a new superordinate generative model. And that's what we call the GLUE model. And ideally, that coordination should produce designs that on a system level should be performant, feasible, and diverse. And crucially, and I just want to stress this again, we can do this with pre-trained and frozen subsystem models. So during GLUE training, no more modification of the subsystem models is needed. So from our point of view, there are two principal ways for training GLUE. The one that you see on the left consists of two steps, and I would say that's sort of the classical approach. And that is to one, use an optimization algorithm in the unified latent space C to find feasible system level designs. And then two, use some large data set of optimized Z's that we obtain with the optimization algorithms and use that to train some state-of-the-art generative model like a diffusion model or a GAN or a VAE. Alternatively, what we can also do is use a differentiable geometry layer to backpropagate a weighted sum of constraints, objectives, and diversity losses directly into the GLUE model. And so in our experiments, we see that both of these methods can work, but the data-free GLUE model, which you see on the right, has some particular advantages when we test it on our UAV test case with 5 very hard to learn constraints. So the first of these is that in our UAV test case, the data-free method is much less prone to local minima than the optimization algorithms. And it pretty robustly collapses to a near global maximum if we don't incentivize diversity. And that's what you see here on the bottom right of the left plot. And we can also sort of confirm this when we look at samples qualitatively, where gradient-based optimization, which you can see in the top row, is rather prone to local minima. And a particular example of this is the middle sample in the top row here. And the data-driven GLUE training tends to replicate this bad behavior since it's just trained on samples obtained with the optimization algorithms. And in contrast, and you can see that in the bottom row, data-free GLUE virtually collapses to near global optima if diversity is not enforced. Second, we observed that data-free training of GLUE directly on the geometry layer, shown here in dark blue, is more than 2 orders of magnitude more sample and compute efficient. And that is because it, one, uses full gradient information at every forward pass on the geometry layer, and it, two, doesn't discard intermediate samples in the optimization trajectory. So our big learning here for this point is that if we want to learn constraints between subsystems very efficiently, it's very, very useful to use full gradient information. And lastly, we find early promising results of what we call basin hopping. And what that means is that the glue models show the ability to traverse infeasible and low performance regions to sort of bridge between high performing good basins of feasible designs. And we think that's a very promising early result. In the paper, you'll also find 2 relevant ablations that I won't go into detail here. So one of them is on the role that the quality of the subsystem models play in all this, and one is on mode collapse induced by quality constraints. So if you're interested in these or want to check out our methodology or more findings in detail, make sure to check out our preprint. And we're also very glad to hear back with any feedback or questions. And thanks for watching.